Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Okay, step on inside. Now, if you have been doing any graphing with me in the past using the letters A, H, and K, and sometimes B, then you'll be on the right track in graphing square root functions and cube root functions with me here today. If you haven't done it, good luck being with me on this stuff here. This is what we're going to be doing today with those things, and you know, maybe you can catch on. Maybe you can catch on a little bit, but it all has to do with you understanding square root behavior, cube root behavior, which I'll go over with a little bit based on the problems. And then AHK, man, if you don't know what those letters are that I'm talking about, I don't know, just good luck with you. Vertical stretches and compressions and reflecting over the x-axis. Horizontal stretches and compressions and reflecting over the y-axis. Horizontal translations, vertical translations. Yeah, all those things, we can do them to any graph that we want as long as we can get them in that form. And that's what part of today's thing is getting the graphs in that form. Square roots first, cube roots second. 12 total problems to do. Let's go ahead and get started. Okay, so in this one right here, we're going to start with 6 square root functions. Now, they're going to start in that general form where they're going to have some f of x whatever. Now f of x in this case is the square root of x. So when I see, say, f of 9x, for example, I will be having the square root of 9x in my equation. Now f of x being the square root of x means, and I'm going to go ahead and graph that first, and then I'm going to erase this thereafter. The square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, and the square root of 16 is 4. Now I chose those specific values because they are perfect square values right there. And those get me some rational values I can work with. I don't care about the square root of 3. For all intents and purposes, it's somewhere right there. Around, it's probably not perfect, but square root of 3 is around 1.7 something, I do believe. And the square root of 8 and things like that. And it's just going to be hitting pretty close to those, or at least as close as we're going to manage. So that's a square root. That's the parent function for f of x equals the square root of x. What if I translated this thing? What if I translated this thing, 10 units to the left, or 3 units down? Or I went ahead and I stretched this thing horizontally, I guess it stretches everything like that. I can't really change these the way I want to. Anyway, what if I do those things to it? That's what our g of h equations are going to be. Now this thing will go away eventually at some point. Maybe I'll keep it there for the first graph to remind you on how to do this. But that's what we're going to do, guys. We're going to graph new equations here based on a new f of x. We got to write what the new equation looks like. And for square root functions, domain and range are important. Why? Because if you noticed, this graph, which is actually like a parabola, by the way. It's like a sideways parabola, but it's only half a parabola there. It stops at some bottom or perhaps some top if the graph goes upside down. And notice it never went, just like parabolas, they have a limited range. Square roots have a limited domain for the fact that this would be, even if it was a full parabola, it couldn't go any further left. You got to think about one of the reasons for square root values. Notice how I said square root of 0 was 0. I didn't talk about square root of -1 or -4 or -9. Because those are imaginary values, and those don't fit on our xy real axes, coordinate plane right there. They don't belong there. They don't show up there. They're not present. You can only go as far left as 0, and that's something we're going to be talking about with domain. All right, so let's go ahead and get started with these problems right here. Let's start number 1. G of x equals f of 9x minus 5. If I were to rewrite this thing, remember that f of x is the square root of x. So g of x is the square root of 9x minus 5. Now I could graph this right here. And like I said, if you're new to my channel with these kinds of things using A, H, and K, in fact, B is present right here, and I'm not going to be really using B. You'll see what I'm going to talk about. I can graph this without use of a table. I'm not trying to plug in values for X and see what values I can get out for Y. What I want to use is the behavior of this square root graphing function and then be able to plot points as needed in really fast fashion. First things first, as far as H and K goes, the HK is your vertex, if you will, of this. I don't know if it's called a vertex. It's not a full parabola, and then I call it a vertex. With a half parabola, is it still called a vertex? I don't know. I'm going to call it that. Cube root graphs, I'll call them a center. Here I'll just call it a vertex. It's a reference point. I'm going to start from there. Anyway, that HK in this case is 0, -5. H is 0. You don't see it present in there. X minus H, there's no minus 0. K is -5 plus K plus -5 right there. So that is where I will start this graph, right? That's a portion of this that I want to really touch on. But the B value currently is 9. We're looking at B as 9. Now, the larger B gets, the more the graph is actually horizontally compressed, because you got to choose X values that are 9 times smaller just to match up with it if this wasn't here, right? If X was 1, then you'd be saying that you'd be getting the same y value out as if this wasn't here and x was 9. So x being 9 times smaller means you're compressing your graph there. So this graph would be horizontally compressed by 9 times. I'd prefer not to do that. I'd prefer to turn it into a whenever I can, and as long as that value is a perfect square, I will go ahead and do that. Spoiler alert, all the ones in the square roots that have something like that in front, like this 9, you see this 4, they will be perfect squares. The cube roots, they will be perfect cubes. I don't plan on doing ones that aren't perfect squares or perfect cubes for now, but if you do, you're going to have to work with a horizontal stretch or compression. Okay, now here's what we can do in this problem here. We can take the square root of 9 times the square root of x, kind of split it up like that, and I won't write that each time, but I want to show you a property that we can give to use right there. Square root of a product equals the product of two square roots, and the square root of 9 is 3. So what this is going to allow me to do is rewrite this equation with a 3 on the outside right there so that my b is absent from this. I'm not talking about horizontal stretches and compressions just because of how weird they can get. Instead, I'm now referring to a. This is an a value of 3, which is a vertical stretch of 3. That way I can still choose my x values and go 1 away, 4 away, 9 away. And I'll just affect my y's instead, which go up consistent amounts of 1, 2, 3. I will now triple those values right there. So 0, -5 is my HK right there. I'll talk about domain and range in just a moment right there. So at 0, -5, this would be the starting point of the graph. So this point shifted down 5 units. And every other point would shift down 5 units as well. But a lot of these points are going to triple their distance from this vertex right here. As I go 1 over instead of going 1 up like this guy, I'm actually going to go 3 up because 1 times 3 is 3. Now I'm getting 3 again from that a. Whoops. I'm getting 3 from that a value, which is a vertical stretch factor right there. Everything that I go up will be tripled. Going 4 over instead of going 2 up, I'm going to triple that, and I'm going to go 2, 4, 6 up like that. 9 over instead of 3 up, let's go 9 up. 3, 6, 9. Notice how it's passing blue, and yes, I will erase blue eventually. And then 16 over, square root of 16 is 4, times 3, 4, 8, 12. I believe it's right there. And that's what this graph looks like here. And that's all I can fit. And I'm happy about that. So I'm going to draw a terrible looking curve there. Let's try that again. I'll start from this end. I think I'm more confident. Not even close. All right. Anyway. Pretend like that ain't that bad. That actually wasn't that bad. Should probably pause and come back. All right. Now this graph does continue forever in this direction, right? As it keeps kind of curving itself off. Boom, boom. Okay, so from there, that is the graph, and those are the transformations from this original f of x. Notice nothing reflected, but it did shift. It translated down, and it stretched 3 times taller there. And that's my number 1. Okay, give me 1 sec. I just got an email I got to check on. Okay, perhaps I didn't get an email. I thought I heard a noise come from something. All right, that's number 1 right there. Now, let's talk about domain and range. Domain, well, let's talk about the original domain and range from this graph. X has to be greater than or equal to 0, and that made y greater than or equal to 0. If you look at the graph, clear as day. The leftmost point and the bottommost point is 0 for x and 0 for y. So it can only go right from there and up from there. Now, you can see this right here as well. It goes from 0 on x to the right and from -5 on y upward. So we could easily say that the domain of this is x has to be greater than or equal to 0, and range y has to be greater than or equal to 0, or f of x, g of x, I should say. That being said, how can you come up with them without the graph? For domain, that's something we actually are going to do often without the graph. In fact, it might even help us do some of our graphs that we're going to have. Domain is based on saying we can't take the square root of a negative, that this guy inside here, and it's not always x. In fact, the next time it won't be. The thing inside the square root has to be 0 or positive, greater than or equal to 0. I mean, literally, that's actually all it is. I didn't have any work there. But whenever it's a larger quantity, we can go ahead and actually solve that thing for domain. Range is a bit of a different story. Part of it's limited on your domain. You could actually plug in your domain value and see what you get out for y, in which case you plug in 0 into here. How about right here? You'll get out -5 for y. And then you'll have to know if your graph goes upward or downward. But honestly, I think that has more to do with your graph. Your domain is based on what you're going to input. Your range is based on what is your output. So input are the values that you choose or that you find out whether there are restrictions or not. Range is what it's limited to based on what you plugged in. So range is a little bit more based on the graph. And I'm not saying you have to draw your graph, but you have to know what your graph is going to look like or how they behave. And square root graphs are limited based on that vertex. that starting point hk. It's really all based on k and whether your graph goes up, like this positive, or down if it was negative. That's supposed to be a plus right there. And this one went up because it was positive. So I'll try and predict range for you. I will happily do it. On this next problem here, so we start number 2. And we'll get to there as we start to clean this thing up. So number 2, right here, this time I got negative f of, so negative square root of 4x plus 8. Now, when it comes to the idea of hk and everything like that, notice that there would be a plus 0 right here. So it looks like k is kind of not involved as far as translation goes. Looks like k is 0. But what is h? You know, last time h was just 0. There was no translation there. And this time, you know, if you've gone along with x minus h's before, you might assume that this is negative 8. Negative 8. Well, it's not, because 4 times negative 8 plus 8 is not 0. We're trying to find the value that makes this 0 that minimizes our value. And that is kind of based on domain. So let me start with the domain concept and see if we can carry it through there. If we look at 4x plus 8, that right there, 4x plus 8, that is what we're taking the square root of. The thing we take the square root of has to be 0 or positive. 4x plus 8 has to be greater than or equal to 0. If you subtract 8 and divide by 4, you're going to see that x has to be greater than or equal to negative 2. Negative 2 is the smallest value for x that I could substitute and still get 0 or positive. 0 in this case. And that, you know, I can take its square root. Anything less, like negative 3, I end up getting like negative 12 plus 8, which is clearly a negative number, something I can't take the square root of. And that ends up being the domain right there. That is x is greater than or equal to negative 2. And you can see how I went about solving that right there. And that does represent h. H is negative 2. Now, I don't see a negative 2 here. How do we bring it about? Well, not by square root, not just yet. No, we have to first factor that 4 out. If you go back to the appearance of our equations here, and I'm going to really ignore the plus 0. But if you go back to our, oh, by the way, negative 2. If you go back to our equation here, notice how b has to be factored out. This needs to be a 1x and a positive 1x to reveal what your h is. And you don't have to do this. I already found out what the domain was based on that, and I could use this as a horizontal stretch and, you know, whatevs, or compression and reflection and all that. But if I want true graphing form, and if I think it's going to assist me best, I'm going to work in it this way. Furthermore, I'm really actually going to be trying to square root that b value and be left with just a positive or negative number in some cases inside the square root. No negatives yet. But I am going to take that square root of 4, just like last time I took the square root of 9. Now there's a negative outside of there, which kind of means negative 1. So when I take the square root of 4 and get 2, 2 is going to multiply with negative 1 there, and outside you're going to get a negative 2. So this g of x equation is going to be negative 2 times the square root of x plus 2, like that. That does leave us with, once again, that domain of x is greater than or equal to negative 2. Those are the values we need in order to get positive results out in square root or 0. The range would be limited based on k. Now, we haven't really mentioned what k was yet. Well, we did, actually. It's 0. But we haven't mentioned which way this graph goes. There was going to be a vertical stretch of 2, but it's also going to reflect over the x-axis there. It's going to be flipping over that way, and we're going to be going downward. So I can predict that this range will be y is less than or equal to 0. We're going to look at the graph anyway, but that's a handsome prediction on that based on the fact this graph should be going downward. Okay, so here's number 2 right here. We're going to start at negative 2 comma 0, like that. Now, the basic premise you're going to want to know to get rational values out is 1, 1, 4, 2, 9, 3, 16, 4 square roots of values. We're going to be going downward instead, and we got to double their heights. So instead of 1, 1, it's going to be 1, 2. Instead of 4, 2, it's going to be 4, 4, as we double the 2. Instead of 9, let's see, negative 2 to 7. Instead of 9, 3, it's going to be 9, 6. And instead of 16, which is at, what now, 14 way. 16, 4, it's going to be at 16, 8, and 8 down like that right there. There's your square root graph. It goes to the right, but it does go downward. Y is less than or equal to 0. We're talking about y's 0 or less than. X is negative 2 or greater than. And that's the domain and range. All right, let's move on. Let's take a look at number 3 right here. Now, number 3 has not much new compared. Well, actually, there is one big new thing, and let's go ahead and get into it right now. So, as a square root function, it's going to look like this: negative 4 times quantity x plus 3, and then plus 1, because f of that. Now, There's a 4 in there, which I can take its square root. The square root of negative 4 is 2y, and that's not something that we're going to be working off of. Bottom line is, I can't take the square root of the negative. I'm not talking about negative 4. I just mean the negative symbol, the negative 1 that's inside there multiplying by that 4. It leaves me with an imaginary result. So I'm going to leave the negative inside there as I take the square root of 4 right here. And I'm going to get 2 times the square root of negative x plus 3 plus 1. Now, I don't care to distribute this negative into here either, at least not for the sake of the graphing form. I can kind of think that b is negative 1 in this case. And again, that's going to be important. There's something I can do with it. It's not like there's no graph here. See, it's not about you can't take the square root of a negative. Well, that's true, you can't. But negative isn't all that's in there. X is in there plus 3. Now, what if x was negative 100? Negative 100 plus 3 is negative 97, and the opposite of negative 97 is positive 97. And I can take that square root. So there are x values you can plug in. They just don't maybe happen to be positive or very large. There are other numbers that we can get. What are they? Well, let's go back to the idea of the domain. Consider your domain where negative x plus 3 as a quantity has to be greater than or equal to 0, right? The thing inside the square root. Even with the 4, you divide by it, you get 0. Now, if I distribute the negative this time, I get negative x minus 3 is greater than or equal to 0. Add 3 to both sides. 3. And then divide both sides by negative 1. You'll get x here, negative 3 here, and a flipped inequality. Oh, dividing by a negative does exactly that. And that's what your domain is here. It's going to be a little bit different from before because this time it says less than or equal to negative 3, which means this graph goes left. It doesn't go right. Negative 3 is the largest number that we can use. And the largest number means that if we go smaller, we're going left. And that's what that b is doing. It flips it over the y-axis here. Instead of going this way, we're going that, or sorry, instead of going this way, we're going that way. Wait, this way, this way, that. I forget which way I'm oriented talking to a camera. It's like talking to students there. I double-crossed myself there. Anyway, so negative 3, and what's negative 3? It's also the h value, right? H is negative 3, and you can see where it shows up there. K is 1. We are going upward, and we're doubling once again right here. This is y is greater than or equal to 1. As we go upward from that, we're going to go and plot that point, and we do have that graphing form here. G of x equals 2 times the square root of negative x plus 3, and then plus 1 right there. So let's go ahead and graph this thing. I'll start at negative 3, 1, okay, as a vertex, if you will. Negative 3, 1 like this. This graph does go left, and you double them heights. 1, 2, 4, 4. I'm at 3. 9, 6. 16. Can't really fit that one. I'm just going to go ahead and leave it like that and go on left like that. There it is. Okay. And there's that graph as we go left. You're lucky we got some whole numbers right there. I think we had a fraction at some point. Not excited for those ones. Okay, number 4. G of x equals negative f. And then there's that, all that stuff. All right, g of x equals negative square root of negative x plus 7 plus 4. Much the same like number 2. There was a 4x plus 8 right there, but the b wasn't factored out to leave us with a positive 1x. Well, this isn't a positive 1x either. That means don't assume that h is negative 7. If you go back to your domain appearance right here, this is something always worth testing, especially when you're new to this, or if they ask you for a domain. When it's greater than or equal to 0 right there, you subtract 7. Whoops. I guess I could have written that. You subtract 7 from both sides, and you divide both sides by negative 1, and you can see that this thing goes left for 7. That means h actually is 7, not negative 7. But I will indeed factor out that negative 1 right here. We'll have x minus 7 right there, and that kind of reveals what we got, plus 4. Now, a is negative 1, and b is negative 1 right there. H is 7, k is 4, all that good jazz, right? But the a and the b, I'm not going to do negative times negative and turn this positive. No, no. If a was positive, we'd go up. If b was positive, we'd go right. This graph goes down and left. That's a way different story there in a different set of x's that we're going to choose that change our y's that we get. The highest and rightmost y is at 7, 4, and that's where we're going to start this thing. First, let's write this thing down. G of x equals negative square root of negative x minus 7 and plus 4, like that. Now, domain, x is less than or equal to 7. As this thing goes downward as well, it's going to be y is less than or equal to 4, or so it should be. So 7, 4. Was there a stretch besides flipping over? I don't think so. I think it's just 1. So 1, 1, 4, 2, 9 from 7 is negative 2. 9, 3, 16. That's from 7 again, so negative 9. 16, 4. Can I fit the next one? What's the next one? 25. 25 from 7 is 18. They're really close because this is 17. I'll pretend like it's, right there, and then down 5 like that. There we go. Not bad. Unless I plotted something else wrong. Pretty good. Well, something might have been wrong there. Hold on a second. What I say was the 16 right here? 16 was from 7. That should be right there. There we go. All right. Sorry about that. It looked like it wouldn't have hit things very well. And that's going to be as best as I think I'm going to be able to get right now. Looks pretty good. Looks pretty good. Okay, there it is. It goes down. It goes left. It is pretty radically different. Hey, radically. That was no pun intended, guys. Seriously. All right, let's keep moseying along. Looks like I got to go back to green. We're going to do number 5 right here. Brand new. Exciting. Let's go. Oh, fraction. But is it? I think it actually stays a fraction. So check out that negative 9 right there in the same way that we had some of these other ones. This is 1/6 times the square root of negative 9 times the factored x minus 5 plus 3. Leave that negative 9 factored. In fact, don't even call it a negative 9. Call it a 9 with a negative 1. Square root of 9 is 3. Let's get the square root of that out there and do 1/6 times 3 right there. And there is still that negative there, x minus 5 and plus 3. 1/6 times 3 is 1/2 when reduced, so our g of x is 1/2 times the square root of negative x minus 5 and plus 3. All right, if you're starting to get pretty good on the concepts of this, we do have a b value of negative 1, which means it flips over the, am I going the right way? This way. Which it flips over the y-axis, which means this graph goes left. The h value is 5. We got to go left to 5. X is less than or equal to 5. This graph goes upward. 3 is the lowest value. Y is going to be greater than or equal to 3. It goes up and left. There's a stretch factor, a compression factor of 1/2. Everything will be half the height from before as we go left from 5, 3. Let's go on to that one. From 5, 3, let's go up and left. Left 1, up half of 1. Left 4, up half of 2, which is 1. Left 9, up half of 3, which is 1.5 right there. Left 16. 16, I kind of wish I had numbers here. Up. Boom, like that. Probably all I can fit for myself. Generally not a fan of the ones that don't show enough character. That's why I was like doubling heights as often as possible. But you know what? Still a square root graph. Going to work out. All right, and I'll move my picture here for the last one as we get to number 6. Okay, number 6. Back to purple. Let's go. All right, 4 times the square root of, here we go, negative 1/16 x plus 1/8. Now, nothing changes in the regard of factoring the thing that is, we got to get our true h and then can reveal b. We can work on square roots, and I'm going to go ahead and do that. That means negative 1/16 needs to factor here. Negative 1/16 needs to factor out of both terms. Now, negative 1/16 times x gets you negative 1/16 x. But what do we got to put here to get 1/8? Negative 1/16 times something is 1/8. Now, keep in mind the negative distributing into there to get a positive means this needs to be a minus right here. So let's ignore the negatives for a second. Let's look at the 1/16 and the 1/8. 1/16 times something is 1/8, which means if you divide something by 16, you get 1/8. That's one way to think about it. If I'm dividing 1/16 out of here, then this thing that was inside had to have been 16 times larger. Because when I multiply it in, I make it 16 times smaller. So what's 16 times larger than 1/8? 1/8 times 16 is 16 over 8, which is 2. A 2 is what goes right there. I'm double check that. Negative 1/16 times negative 2. See if you get 1/8, but that's what happens. Generally when we factor, like this 4 way up here, You factor a 4 out, and you divide 8 by 4 right here, and that's what we're doing here. But dividing by 1/16 is multiplying by 16, so there you go. All right, so there's that part right there, but I'm still probably not done with this. I do have a negative, which I'll leave inside, but the square root of 1/16 is actually 1/4. Square root of 1 is 1, square root of 16 is 4. 4 times 1/4 is 1, and you are just left with square root of negative x minus 2. Do I have a graph like that before? Square root of negative x minus 7, sort of. All right, this graph does go left once more. Domain is x is less than or equal to h. R is y is greater than or equal to k. Let's graph that. No stretch or compression to speak of. The hard part was the getting in that form, but I'm avoiding tables, and I'll go whip fast. 2, left of 2, up from 0. So we're going 1, 1, 4, 2, 9, 3, 16, 4. Bada boom, bada bing. All right, and that is our last square root graph right there. Are there questions for me? You may have some. All right, the next graphs we're going to be doing, and the final ones here, in fact, are cube root graphs. And in some ways, they're easier. I mean, the graph itself, I'm going to talk about f of x equals x cubed to begin that process, right? We'll kind of get into that. And I'm going to be getting those b's out there, including the negative this time. Now we're going to talk about how that's going to work. Starting by talking about cube roots. Let's draw the parent graph of that thing. The cube root of x looks like the cube root of 0 is 0. The cube root of 1 is 1. The cube root of what is 2? That'll be 8. 8. That's a perfect cube. 27 is actually the next perfect cube. Cube root of 27 is 3. And this doesn't go all the way to 27, not unless I want to graph on this one right here. And I'm not going to. But here's the thing. We can cube root negatives. So I can actually go to the left on this graph as well. Just like negative 1 cubed is negative 1, the cube root of negative 1 is negative 1. And the cube root of negative 8 is negative 2, and the cube root of negative 27 is negative 3. So that's all I can really fit right here. And I'm going to go ahead and do the best I can with that. But of course, this will not be, I'm going to have some trouble with some of these graphs here. You're going to have to forgive me on the nature of my drawing. All right, that's a very squiggly, poor, but general cube root graph, and that's the idea. Kind of that snake through thing. We've seen them with cubics like that, and now their cubics are inverses of cube roots. So that's going to be the general idea of it. 1, 1, 8, 2 are the values we're going to look at. Maybe a 27 here or there if it actually fits. I can't remember. I have no idea. And then we got to stretch and shrink some, reflect and things like that. But it goes forever left and right. It goes forever up and down, less so than left and right as far as how fast it goes that way, but it does. They go forever up and down, left and right. Domain and range are all real numbers. I'm not going to ask you for those. But we are going to start with number 1 the same way we did before. G of x equals f of 27 times the quantity x minus 2. Now it's a cube root. So we're going to do the cube root of 27 times the quantity x minus 2. 27 is already factored, and you can therefore take its cube root. And you actually can. It's a perfect cube. It is 3. So 3 times the cube root of x minus 2 is actually our equation right there. That's not 3 cubed. That's 3 times the cube root of. Let me put a little dot there. All right, so your a value is 3. That's going to be a vertical stretch. We're going to be at 2, 0 for the HK. 2, 0 for our center. Not a vertex anymore. I don't even know if the first one officially is, but this definitely is not. 2, 0, draw it like a cubic 1, 1, 8, 2, or cube root 1, 1, 8, 2, tripling the heights. So we will be at, what was it? 2, 0. We'll start at 2, 0 right here. And 1, 1, 8, 2. Let's triple those heights. 1, 3, 8, 6. We'll go left as well. 1, 3, and down. 8, 6. Now there would be another one that's like 27 away and such that would hit 9. So we shouldn't go as low as the negative 9 down here, at least not yet. This thing should still be on approach to there. So probably doing something, right there. Let me just get the in-between part first and see what that looks like. Okay. So you can see how it flattens out a lot more to approach there. Not in full, right? This isn't a logistic curve. You got to look up what that is. It's not a logistic curve with asymptotes. It's It's still working its way down, but you're going to have to give it some time. And I'll leave it like that. Okay, number 2. Another cube root. Here we go. G of x equals negative... Oh, I had to change this. I'm sorry. This is negative 1/8 x, and I don't think I changed it in my other PDF thing. I got to do that. All right, that should be a 1/8 inside of there. So here we go. G of x equals negative cube root, excuse me, of 1/8 x. Cube root of 1/8, I think we saw a cube root of square root of 1/16, which was 1/4. Cube root of 1/8 is 1/2. So this will be negative 1/2 times the cube root of x, like that. Negative 1/2 times the cube root of x. And, I'm going to call more attention to the, I didn't mention it in this one. I haven't mentioned it in a while. B values can be utilized. We could have said horizontal compression by a factor of 1/27th. Could have been 1/27th the size horizontally like there. I'm not really dealing with them that way, but, you could. This would have been a horizontal stretch by a factor of 8. We would have been 8 times wider that way, and not bad, but you'll kind of see why I also might not want to do that. I'm going to go ahead and do the vertical compression by a factor of 1/2 here. So 1128 stuff. We're going to start at 0, 0 this time on number 2. Let's change this color. 0, 0. It will be going downward as we go right. That's what the negative was doing out in front. And we're going to be going down half of what we normally would. Instead of 1, 1, we'll be going down 1, 1/2. Instead of 8, 2, we're going to go down 8, 1 like that. And then 1, 1/2 right here. And then left 8 up 1 right here. Now, these points are pretty nice to help you show the outward curve of this thing so you don't accidentally start going another way. And that's something that I want to bring up when I'm talking about the horizontal stretch. Good enough. Okay, so here's the thing. If I did the horizontal stretch only, where B was 1/8, then I could say, okay, horizontally stretch by a factor of 8, which means instead of going 1, 1, I'd be going 8, 1. And by going 8, 1... that means I skipped this point right here where it goes 1, 1/2 and things like that. And skipping that means that I don't have any other point to base this thing off of. I only have this point, and the origin. And who knows what other people would draw. Some people might draw something linear like that. Some people might draw more of a cubic where it goes up this way and down that way. And that's not what it does. I think these points really help assist that, having those by nature. So instead of stretching and compressing, I'm just going to do what I did there, and that's fine. All right, let's go to number 3. And actually, hold on. Let me pause. I got a text. Give me a second. Okay, it's one of those political spam texts. That's what they're texting at 9:20 at night. All right, number 3 right here. G of x equals f of 8x plus 24. Cube root of 8x plus 24 plus 2. Hey, let's factor the 8. Got to factor that thing before you do any cube root business. Can't just turn this into a 2 and then say that's still 24. No. The 24 is just, it's a part of it, right? You got to, I guess I got to rewrite it. You got to factor that 8 out before you can take its cube root. The real value inside there is 3 before you work on that cube root. Cube root of 8 is 2. We get 2 times the cube root of x plus 3 and then plus 2 like that. All right. I did a 3 before, so this is a 2 now. Let me make sure I was doing a 3. Yep, 3, 3, 3. Okay. All right, so right here, stretch factor of 2, vertical stretch factor 2. It goes right and up and down and left. We go to negative 3, 2 for our center. So number 3, negative 3, 2 is our center. 1, 2, and 8, 4. 8, 4. Still can't fit 27. I can't imagine I didn't actually put one where I couldn't fit the 27 over. Like if I go 10 over or something like that. Maybe it leaves out some idea of symmetry because you can't really see both ends of all the points that you're trying to get. But that's okay for one problem. Come on now. Come on, Mr. Robinson. You did make this worksheet after all. Was last year though. Why not make a video last year? I don't know. We did this as an in-class activity on like a block day. All right, I'm gonna go ahead and treat that. That's fine. Okay, that's our number 3. All right, notice how, again, domain and range are all real numbers. I don't have to limit myself that way. And now we are dealing with our first negative inside of here. Let's see what that does. Number 4, g of x equals cube root of negative x minus 10 plus 4. Okay, definitely not going to distribute the negative here, and I don't have to talk about domain right here either. No flipping inequalities. X doesn't have to be positive or 0. It can be any value. But do I want to keep this negative inside of here? As you know, the cube root of a negative value is also the negative cube root of a value. Both of those work both ways, which means I can just bring that negative 1 out here. It is literally a cube root of negative 1 that I'm dealing with. That is negative 1. I'm going to go ahead and do that, but it doesn't harm us either way. I'm going to put it out in front, and I got cube root of x minus 10 inside there, and then plus 4. As long as, if we see things as a, h, and k as often as possible, I think that'll help us. But, consider that a negative inside of here means it takes some graph and it flips it horizontally. Now, I'm going to literally use a feature that has me flip horizontal. You're going to kind of understand that. Boom, right? It flipped horizontal right there. Well, imagine that my curve was perfectly drawn as I would. If I flipped it upside down instead, boom, I still have it go in that direction. And yes, I did flip this one upside down versus the other one I flipped left and right. So, just kind of get that understanding of what's happening. It's the same graph, whether you flip it over the x-axis or y-axis when it's a cubic. Quadratic's a way different story there, but that's why the negative can apply to one or the other. I brought it on the other. Brought it outside. So to go down and right, up and left, we're going to go to, 10. We're going to go to 10, 4. 10, 4 right here, which means we get to play with 27. So 10, 4 is right here. This thing goes down and right. So 1, 1. 8. Oh, 8 doesn't fit real well. Sure it does. 8, 2 right there. And here we get to go 1, 1. 8, 2. And 27. All the way here. 27, 3. I can actually fit it. You can see where that lack of symmetry kind of comes through right here. When I get to go really wide on one side of the center, and the other side of the center, I just get to just go like that. Not as enticing, but I fit it. Plot as many points as I can fit there. Hey, we got 2 more problems to do here. And I imagine they're the harder of them as far as like factoring and things like that, but let's go and check it out. All right, number 5. Oh, negative 1/27. Not bad. We just talked about 27 being pedestrian. Negative 6 times the cube root of negative 1/27 x and then minus 1. Cube root of negative 1/27. Remember, the negative can come out with it. It's going to be negative 1/3. Negative 1/3 times negative 1/3 is 1/9 times negative 1/3 is negative 1/27. And then cube root of x minus 1. Negative 6 times negative 1/3 is negative 6 divided by negative 3, which is a positive 2. So we are going to get 2 times the cube root of x minus 1. It's one of those ones where it's easy to graph if you kind of follow it along. It just kind of takes a moment to take care of the stuff inside. And, once we did, we're there. So number 5, 2 times the cube root of x minus 1. Minus 1. 2 times the cube root of x minus 1. The minus 1 is their k. There was no horizontal translation, so down 1. And then double heights. So 1, 1, 8. 1, 2, 8, 4. And the 27 is out again. Like a light. Okay. Apologize for the rush job, doing what I can. Okay, we got one more graph to do, number 6 right here, and that will be based on, well, us going ahead and I think it's a fraction one. I bet it's a fraction one. Why not? I don't know about the end result, but yeah, factoring out a fraction inside there. So we saw that on the square root one. Let's give it a look right here. This is going to be 2 times the cube root of negative 1/64 x plus 1 over 32. Looks like things should clean up just fine. Plus 5. All right, let's factor out a negative 1/64. Inside, we're going to have x. Looks like a minus, right? 1/64 times 1 is 1 over 32. You divided 1/64 out of 1 over 32, so you're multiplying 64 by 1 over 32, which is 64 over 32, which is 2. I think the last one was a 2 as well. Double check that. Make sure you get 1 over 32 from that, and plus 5. So Still not done. I don't want to horizontally stretch this by a factor of 64. I can't fit that while vertically stretching by a factor of 2. One more time, you can see the benefit of, I don't want both a and b. Unless it's just the b is -1 and a square root, I don't want both a and b. 2 gets to multiply by -1/4. That is the cube root of -64. Now that I got it out of there, x minus 2 remains, and there's a plus 5. And 2 times -1/4 reduces to -1/2. And we got the cube root of x minus 2 plus 5. Not bad, dealing with a 1/2 again. In fact, didn't we have -1/2 x? Maybe not. Oh, yeah, we did. Or cube root of x. Yeah, so it's going to look like this graph on number 2. I'm actually going to even copy it over. Only we got to go 2 right and 5 up. So I'm going to take number 2's graph right here so I can be done. Right there, just kind of group it, copy, and paste. And let's go ahead and bring that thing down. And I think I said 2 right and 5 up. And that's what your graph should be looking like right there when all's said and done. Right, hold on, 2 right. Yes, 2 right, 5 up. So boom. All right, so that's what I was saying. Cube roots might be a little bit easier. You don't have to deal about domain, and you can take out those negatives whenever you want to, and flipping it horizontally, same as flipping it vertically. But you still got to work those numbers there. They're going to be a little bit bigger with the 8 and the 27 and things like that. You got to know it goes left, right, up, down, all that kind of stuff. All right, guys, but that ought to do it for this one here. This is Mr. Robinson. Thank you so much for watching, and whew, it's been a long day for me, so I'm glad to get with it done, too. Eyes are bloodshot, man. Been out in the sun forever. If you want to see more, just stay tuned for more. Ask me questions in the comment section down below. And take care. I will see you in the next one.